Last time I kind of weaseled out on trying to do a third degree, third order, that number 36 that we saw. So Chun Li said it was all okay. You did it right. So I also ended up doing it, and I made a recording of it, so I'll post the video online. But the trickiest part in doing this is coming up with the third derivative. And the third derivative gets a little complicated, but it's not impossible. It's doable, and we just have to remember is that the derivative of y as a function of x is going to be y as a function of t, and then t is a function of x. So there's a chain rule that's involved there, and so the chain rule happens in a couple of places. The first time it happens when you just take the first derivative is the chain rule here, the dy dt dt dx. And whenever we come up with a dt dx, which is what we're going to come up with a lot when we're taking derivatives of derivatives of derivatives, is that since we know that t is equal to ln x, the derivative of that is 1 over x. And so that comes up a couple more times in our second derivative. It comes up over here where we take the derivative of dy dt. The derivative of dy dt is the derivative of dy dt, the second derivative of that, and then we need to take the derivative of the t with respect to x, which is a dt dx. So, I don't know. Can you guys check back there, see if you see any keys? You were sitting back there, right?
Yeah, but my back.
No? No loose keys on there?
No.
Could you have left it on the way out? I could drop this somewhere?
But it was in my phone.
Okay, sorry. Yeah. So that derivative happens a couple more times when we're taking derivatives of derivatives. And so you can take a look at, I'll make this document a PDF and upload it also. Anyways, once you got done with that, you'll see that when you replace the third derivative, the x to the third power will cancel because you have the 1 over x to the third. And you replace the second derivative, that would also cancel out the x squareds, and then you'll have some constants. But the bottom line is that in doing this substitution, you would have effectively changed your problem from a Cauchy-Euler differential equation into a differential equation, a linear differential equation with constant coefficients. So you do this, and then because this is a third order differential equation, you're going to get a third degree polynomial, and then you just have to try to solve for this using whatever you can. And so if you just take a guess at possibly 1, 2, or 3 might be a solution, then you can do some, dividing polynomials, divided by m minus 2 or m minus 1 or m minus 3, and then you can reduce it, and then it'll be a quadratic. Or you can just plug it into Wolfram alpha and find the solutions. So the solutions are 1, 2, and 3, and since this is a problem with constant coefficients, our assumed solutions will be e to those powers, and then we have 3 distinct roots, so it'll be e to each of those roots. But this is y of t, and our original problem was a function of x, and so you just need to replace the t's with the substitution, which is ln x, and then you can simplify that to this. So that's the process of doing that substitution. Now, instead of doing the substitution, if you would have just took the Cauchy-Euler approach where we assume that your solutions are x to the m, you find the 3 derivatives, and then you plug that in, you get your you get your auxiliary equation, which is coincidentally or not coincidentally exactly the same as what we saw earlier. And then you would have your solutions this way. Yeah. No, so I don't know if you asked that same question or somebody, yeah. So, but I think the reason for showing that, is because of the similarities and the special case that Cauchy-Euler really is, and how it's related to the constant coefficients. Anyways, I went off and finished the rest of the problem by finding the particular solution. You can watch that in the video. Yes, I'll post it sometime today or tomorrow. It's already done. I just need to, put some headers on this file and then upload the video on YouTube. But I'll post that. All right. So we are now in the next section. And the next section is really just a way to simplify the process that we've been dealing with all along, and that is to simplify the variation of parameters into a function, and this is called Green's function. So we're solving for, we're going to focus on second-order linear non-homogeneous differential equations. And the particular solution that we saw was y1 times u1 and y2 times u2, where y1 and y2 are solutions to the corresponding homogeneous, and u1 and u2 are obtained through the Wronskian. Some weird formatting issues here. And so what we're going to do is we're going to introduce Green's function that will allow us to help us quickly find our particular solutions through this function. What? Eco-friendliness. So what we're doing here is we're just trying to streamline our process. And if you remember what we had before, we had our W1 is equal to, remember, we replaced the first column by 0 and the function, and then we keep the second column the same. And then when we find the determinant of that, we're going to get 0 minus y2 times f, or y2 times f of x. And this is exactly what goes in your numerator for u1 prime. And so, like I said, this is just a streamlining process. And you'll see the same thing is going to happen for W2. So this is really the determinant of that second matrix that we have. And now here, instead of just saying we're going to integrate, we're going to talk about integrating and then putting limits here, where x naught is eventually going to be our initial condition, x value for our initial condition. And this will help us find our particular solution a little bit quicker if we have an initial value problem. Okay, so I think there's a few more, I guess, a formal definition here. Green's function for initial value problems is going to be given by this. So if we let Green's function, so this is our formal definition for Green's function. So Green's function is a function of two variables, x and t. And the t is going to be the dummy variable that we're going to use in the integral. So our integral is going to be an integral of t. And then we're going to assume x is a constant inside this integral process. But in the end, what's going to happen after you do the integral is that the x is going to be gone. Or I'm sorry, the t, the dummy variable t is going to be gone. And then you'll just have all the functions with x in it. So if we imagine the y1 being constant with respect to t, we can, constants in an integral, you can bring that inside or outside of the integrand if you want, or the integral. So we can move it inside, and then we can have Green's function defined this way. Okay, see what happens? The fx was pulled out of Green's function, and then, it's part of Green's function when we integrate, but we pulled it out of Green's function, and then we're going to put it back in here when we're integrating. So let's try to do a problem using an initial condition and see if we can find a particular solution. Okay. All right. Let's see, example. Oh, I guess we should copy this theorem too. So this theorem just allows us to use Green's function to solve initial value problems. Control shift greater than sign, and then less than sign, a decrease. All right, example. Let's do an example. Where am I going? Oh, still navigating through this. Maybe we should start off with number 19. All right, what is it again? Window Shift S. Yeah, I'm used to this. With the window shift. All right, let's see what we can do with this. I forgot Green's function already. How's it go? So let's identify Green's function just so we can try to identify Green's function. And it has something with an x and something with a y and a t. All right, yeah, that's helpful. So y1 has a t, y2 has an x, and then they switch orders, and then divided by w. Okay. So what is it again? y1 has a t, y2 has an x, and then there's a minus sign. Order matters, so they switch. y1 now has an x, y2 has a t, and then the Wronskian is a function of t. So we need a handful of things here. Looks like we're going to need the y1, the y2, and the Wronskian. So let's try to find that. We have a second order differential equation. So if we take a look at the homogeneous part and solve for find y1 and y2, that can get us going. So we have constant coefficients. So we can come up with the auxiliary equation, m squared minus 4 is equal to 0. So m is equal to plus and minus 2. We have two distinct real roots. That'll give us a y1 of x to be equal to e to the negative 2x. And then y2 of x is equal to e to the positive 2x. And those are our fundamental set that would solve the homogeneous differential equation. So it looks like we're going to need the Wronskian w is equal to, the order is going to matter now since you've assigned w1 or y1 and y2. So let's use negative to be the first function and then the positive to be the second function. So taking the derivative, we get those constants, negative 2 and positive 2. And then the determinant is 2e to the negative, we add the powers, I think we just get 0, minus negative 2 e to the 0, which is a constant. That's always nice when your Wronskian is constant, so it doesn't play too much of a part in the integrals that we're going to have to do. So we got Wronskian is equal to 4, and I think we're ready to set our Green's function here. So Green's function is equal to e to the negative 2t times e to the 2x minus e to the negative 2x e to the 2t divided by 4. Okay. So, wow, that's it if I was asking for Green's function, but you want to solve for this, so let's see. We have to now put this into the integral to get our particular solution. So y sub p is equal to, according to them, it's equal to the integral from 0, x sub 0, would be 0, our starting point, our initial value problem, initial point, to x, which is a variable right now that we're setting to be a variable. And then we're going to slip this Green's function that we just saw. We got 1/4 times. Now you can decide to put this together or keep it apart if you want. Doesn't matter. This would be e to the minus 2t, e to the 2x, minus e to the negative 2x, e to the 2t. Times the function. We also have to multiply this by the function. E to 2x. Oh, the function in terms of t, yes. dt. So let's see if we can make sure that we understand what's going on here. In the integral, this is Green's function. and this is f as a function of t, and then we have the dt and the integral and the limits going from x naught to x. Okay, so those are the pieces of the puzzle. And then we just integrate, I guess. Yeah, so if there's anything that we can simplify and whatever. So the e to the negative 2t and e to the positive 2t would just go away, and then we can have e to the 4t over here. So let's rewrite this integral going from 0 to x, so 1/4. Suppose we could take the 1/4 out already. I'll do it later. E to the 2x, which is constant with respect to t, and then minus e to the negative 2x e to the 4t dt. So let's integrate. F of t is part of not Green's function, but when you're finding the particular solution for Green's function, it's going to be Green's function times f of t. Oh, f of t comes from the original, the non-homogeneous part. This is f of x as a function of x, and we just change the variable to t. All right, we are here, and we're going to integrate. This is a constant with respect to t, and so what's the integral of 5t x times t, right? E to the negative 2x is constant with respect to t. We integrate e to the 4t, and then you would do a u substitution or something like that. U equals 4t, and then you divide out of 4. So there's an extra 1/4 that comes out, not counting the 1/4 that's outside. Okay? And then we want this to go from 0 to x. Is that good? So let's just put 0 and x there. Seems easy. Try it. No, this isn't too bad. Let's put x in there. We get a 1/4 x e to the 2x, and then we have minus e to the, now this is, we put x in there, this is going to be negative 2x plus 4x. And so that would be 2x. And then let's put 0 in there. You get 0 because t is equal to 0, and then we have a minus e to the negative 2x times e to the 0, which is 1. And don't forget the 1/4 that I keep forgetting. So now we're dealing with essentially a definite integral. And then we can just simplify everything out. Can we combine anything? We can combine, no, I thought we can combine these two, but we can't. So it looks like we're going to have a 1/4 x e to the 2x minus 1/16 e to the 2x. And then here we have a minus, that's a positive, and then a 1/4 and a 1/4. That's 1/16 e to the negative 2x. at your particular solution. Okay. You know what we forgot? We forgot to solve for the homogeneous part. Yeah, we never really finished that because this is an IVP, initial value problem, so we should probably think about solving for the other part. But before we go on, this is your y sub t. Is this clear? Clear as mud? Clear as vodka. I heard that on TV. What? Do we have vodka? Oh, yeah. You can always drink some vodka to make this feel better. Or scotch. I drink scotch. It's not as clear as vodka, though. Yeah. Clear as scotch? Well, yes. No. This will work for third. Oh, Green's function is defined for second order only. Yeah, because the third order would involve like 3 things, and so they don't have Green's function. No. Yeah, no, they don't come up with another name. Kind of. Anyways, we're not quite, we didn't quite finish this because I forgot to deal with the first part, which is the homogeneous part. We have to deal with the y sub c, and it isn't too bad because it's something that we've dealt with already before. So y sub c is equal to c1 y sub 1 e to the negative 2x plus c2 y sub 2, which is e to the positive 2x. And here we get to use our initial conditions to solve for the arbitrary constants. So we need the derivative, which is negative 2c1 e to the negative 2 plus positive 2c2 e to the 2x. That's negative 2x. So when we put 0 in, to the original function, we're going to get c1 plus c2, and that should equal to 1 according to this. And then the derivative evaluated at 0 is going to be minus 2c1 plus 2c2, and according to this it's equal to negative 4. So we have 2 equations and 2 unknowns in our system. Is something that we can do easily, or do we need to do some stuff? Anybody solve for this off the top of their heads? Should we use Mathematica or Wolfram Alpha?
Right away, you get to do -4 is equal to 2c2 plus 2c negative. So you just end up with 4 negative 4 equals 4c2.
All right, let's see if we get the same answer. What the heck is that? I guess we could just use x's and y's. Three halves and negative 1/2? No?
Probably right, yeah.
If I entered it correctly, it should be. I mean, this is Mathematica after all. They work, so it must be right. Oh, you dropped the negative sign? Yeah. Yeah, so C1 plus C2 is equal to 1. Minus 2C1 plus 2C2 is equal to negative 4. Yeah.
Okay, so those are what I got. I just did it wrong.
That's the solving part, right? Oh, too big. You could, but I think that's going to be too long. I think because you're going to have to carry the YP around as you're solving for the C1 and C2. And so I think that would end up being more work for you to try to solve C1 and C2 to get the same result. Oh yeah, that's true. They would all go to 0 anyways. Because you would put that into the original function and its derivative, and this is supposed to, according to the differential equation, is supposed to be a solution to when it's equal to 0. So it should all, this part should all equal to 0. In here? I don't know if it did it? Oh yeah, it did. Because this is going to be 16 minus 16 plus 16. Mm-hmm.
So
C1 is equal to 1 minus C2. Did you say drafts? All right. Darn rats. EGATs. EGATs. Wow. So the solution looks like it's going to equal to C1, which is 3 halves times e to the negative 2x. And this looks like it's a minus 1 half e to the positive 2x. So this is the homogeneous part, the y sub c part. And then now we just copy the rest of them. 1/4 x e to the 2x minus 1/16 e to the 2x plus 1/16 e to the negative 2x. Yeah. Oh. Yeah. I don't know. Did Susanna, didn't you do this and then you were getting the wrong answer? Okay. Oh, what happened? Why does this keep popping up? I don't want you to look at my email. Yeah, so Victor just brought up this idea, and I don't know if you guys, when you guys are trying to solve for those non-homogeneous general solution, sometimes you get some terms that are like terms, right? And if this had a C in it, C1, then this 1/16 could emerge with the C1 or whatever. And so I think you can combine these two. And Erica, I don't know if this is related to the question that you had about putting in the y sub p and then solving for but I think you can combine those constants if you do it the way you're thinking about doing it, and I think it'll work out to be the same. So we can combine these constants together, or these coefficients. No, that's not it. I had a double underline, so these two are double underlined. So you can combine them, and you can combine these two because they have an e to the negative 2x. All right, so let's rewrite our solution to be in a more simplified version. Let me write this out first. The 1/4 x e to the 2x, and now let's get to the negatives. That would be 25/16 plus. It's times 8, right? So 24 plus 1 is 25. 25/16 e to the minus 2x. And then here we have a negative 1/2 plus 1/16. So I think that's 8 minus 1, 7, negative 7. Oh, they're both negative, sorry. 9/16. And this is a positive 2x. Thanks for bringing that up, Victor. So I don't know if they would mark you off wrong in the homework if you didn't simplify or didn't combine the like terms like this. They're usually flexible with that because they run it through Mathematica to check their answers anyways, but they might actually look for you to simplify it. So just be careful with that. Yeah. Yeah. Oh, that's that? Oh. Wow. None of them work. How's your homework like? No, look at this one. This one has should we try that one? Yeah, it looks like we do have a boundary problem. Well, should we do? So this one's a Cauchy-Euler equation. So just be careful when you're working that out. It'll finding your I guess there's a couple of things to watch out for this type of problem. This is a Cauchy-Euler, so when you find your homogeneous equations solutions, you would do one of two ways. The easy way, I guess, is to let your answer be equal to x to the m, and then you find your solutions that way. But when you're trying to find the particular solution using Green's theorem, you have to divide by the leading coefficient here, because the coefficient of the highest order term should be 1. So you have to make sure you divide that out. Yeah. Integration by parts? Okay. You can give it a shot. Guess you'll have to enter your answer to make sure it's right or not. Because it has a pattern. All right, let's try number 5, and then hopefully after doing number 5, we'll still have enough time to take a look at the boundary problems. So here we have they're starting to call this an external force or forcing function, and we'll see in our next chapter when we apply these methods to the differential equations. We'll try to put it in some context of springs and forces and friction and stuff like that. So the tricky part here is our f. Our function is a piecewise function. So basically what that means is that when we integrate, we just have to integrate into different pieces. So we're going to go from 0, that's our initial point, our x naught. And here, if it's bigger than 0, it's one thing. If it's less than 0, it's another. So we just have to adjust our answers accordingly. All right, let's work with our homogeneous portion first. We have y double prime minus y is equal to 0. We got m squared minus m or 1. And then so we got plus and minus 1, which means our y sub 1 would be e to the negative x, and y sub 2 would be e to the negative or positive x, 1 times x. And since we're here, we might as well solve for our initial conditions, our unknown constants, or y sub c is equal to c1 e to the negative x plus c2 e to the positive x. And our derivative is negative c1 e to the negative x plus c2 e to the positive x. So it's 1/2 what? 6 and 3? Yeah, when we get it equal. So we got to put 0 in. We're going to get c1 plus c2 is equal to 9. And when we put 0 into the derivative, we're going to get negative c1 plus c2 is equal to 3. So c1 is equal to 6. c1 is 3. 3, c2 is 6. Okay. We can use Kramer's rule if you want, but it's just solving for 2 equations and 2 unknowns. And so the easiest way, you can even guess if you want, like we can do here. And if guessing doesn't work, then just go through the process of whatever you learned in algebra. All right. So now let's find. We got y1 and y2. Let's use this to find Green's function. We need a Wronskian. And the order matters now that you've assigned y1 and y2. So the first column will have e to the negative x. The second column will have e to the x. And then its derivative. Yeah. Yeah, it seems like it, but somebody brought up, one of these Brians, he said that because it's an answer, because it's a solution to a homogeneous differential equation, when you put it into the differential equation, it'll be 0. And so, in fact, our theorem actually said that they call it y sub h now. Y sub c is going to be a solution to this homogeneous initial value problem. And then y sub p is going to be the solution to this. Oh yeah, notice that it was zeros here, because it didn't really matter what we were plugging it into. All right, so back to our example. We're looking for the Wronskian. We got 1 minus -1. So another nice Wronskian. We got a constant. And Green's function, g of xt is equal to y1 of t. So the y1 is negative, e to the negative t, e to the positive x minus e to the negative x, e to the positive t, divided by 2, our Wronskian. And then we put this in our integral now. And so that just means we're going to have to do 2 of them, but our integral is not going to be bad. So let's try the one where x is less than 0. For x less than 0, we have our y particular solution is going to be the integral from 0 to x. And then our integral from 0 to x of Green's function is going to be 1/2 e to the negative t e to the x minus e and negative x e to the t times, we're assuming that it's less than 0, so it's -1. That's your f function. And then there's a couple of other things about the integral that we probably should address. The fact that this is going to go from 0 to x, and x is a number less than 1, probably means we can switch the order of the limits and then throw in another -1 in there. John, was you going to say something? No. Was it that you were going to say? Yeah. X to 0. So we can write it from x to 0 with a negative in front, and then there's a negative out here too. So I'll put the negative and the 1/2 together, and we'll just remember that that's going to become positive later. Where are we? E and negative t e to the x minus e and negative x e to the t dt. So let's integrate that. We got a positive 1/2, and then we have negative e to the negative t e to the x minus e to the negative x e to the t. Let's see what happens when we put in x first, and then we'll put 0 in. So let's put x. It's negative e to the negative x e to the x minus e to the negative x e to the x. That's just 0, isn't it? No. Yes? It's 2. -2. And then we have to put 0 in, our top limit, in for t. So we have what? I switched it. when I switch these two, I throw a negative sign out of the integral. Oh, so x goes first, right? No, which one goes first? The top goes first. Oh, sorry. Oops. The top goes first. Sorry about that. You got turned around. All right. So we put the 0 first, and then we put the x. So we have negative x e to the x minus e to the x e to the x, negative x. One of them is negative. All right, so putting 0 in there, we get 1/2. We put 0 in there, we're going to get that to be 1. That's negative e to the x minus e to the negative x. So that's the first part. And this one we said was 2 or negative 2? Negative 2. So this will be negative 1/2 e to the x minus 1/2 e to the negative x plus 2.
Oh, wait, no, it usually gets multiplied by 1/2 also. So
that turns into a 1. With opposite signs, it must have something to do with switching the limits. I don't know if we should have switched the limits. Maybe we shouldn't have switched the limits. It just got confusing. Yeah. Zero to x with positive signs. Where? Here? So 0 to x. That's true. Yeah. And then it'll work itself out when you plug it in. All right. So I think by doing this, I maybe lost track. Yeah. This one? I usually put the number with the coefficient that's less first, but it doesn't matter as long as you're consistent. So once you write this out, then you have to follow along with whichever one's y1, y2. You could have gone y1 is equal to e to the x, and then y2 is equal to e to the negative x. And then, but as long as you follow through with the same sides, then that's going to be okay. The t and x's have y1 and y2 next to them also, as long as you're consistent. So I think it still won't matter because there's still consistency to that. So the y1 has a t and y2 has an x. So when you do all this and work it all out, it should be the same. Oh, just this is how the formula is set up. I'm just kind of following the formula. I wouldn't do it like that because you might come up with a negative sign because the order will matter here. So you don't just switch the y's and the t's. You have to actually put the y1 of t first. Oh yeah. All right. So we were in the middle of this. Jong, maybe tell me where I could possibly be wrong again. So there's a negative sign from the function here. From x to 0. But then yeah. Right. Well, it also depends if your function's above or below the axis, and the integral will be positive or negative depending on that.
So when we flipped it on this side, we, the very first expression should have negative. No, it should not. No, it should not at all. So she has to go with from x to 0.
So, but when we switch the order, this negative sign is going to be important. So this should be x is 0. I don't think so because. All right, well, let's try to keep it like this for now. And if we're wrong, we're going to be off by a negative sign. Yeah, I mean, if we did everything correctly after that. So let's say this is our solution. And with our y the y sub h that they're calling it now, we used to call it y sub c. We should have our solution for this. So y is going to equal to the c1. That's 3, and then e to the negative x plus 9 e to the positive x minus 1/2 e to the x minus 1/2 e to the negative x plus 1. It looks like we can combine. We have 3 minus 1/2. That's 2.5, right? So 5/2 e to the negative x. And then the 9 minus 1/2 is, what is it, 8/2? 8.5. 16, 15/2. Oh, sorry. It was a 6. Let's try that again. 5.5 is 11 halves. Okay. No, positive. Yeah. All right. Should we check it now? And so if this was wrong, then this should have been 7/2 and 13/2. And a negative 1. All right.
I've got the other answer. I'm still hoping that I did. Oh, and that was only if x is less than 0. So we find out if x is greater or equal. Yeah. Really.
What happened?
Yeah, you weren't locked in. Isn't that the best? That wasn't even that long though, so you're lucky. It's really great when there's like 5 terms in there. Stupid things going on. You press it and it disappears. You're like, oh, sure. Control A, copy. Oh.
So, what happened?
So you have to write 0 to x, like the formula says. Can't go with x to 0.
So yeah, I guess that's the thing, is that the initial value has to be in the bottom, and whether it's from the bottom to something positive or from the bottom to something that goes negative, like in this case, we have to have 0, because the formula is looking for x naught to be at the lower limit of your integral. And so I think that would be the explanation for why we want to make sure that this is 0, regardless of whether x is positive or negative. All right, now you guys can do the other part. So the other part's almost the same, except your function here would be positive 1 instead of negative 1, and then you would walk through the same process, which I think would give you the same answers, except the answer that we were looking at, right, with a negative. Hell, might as well type it in. Let me see if it works. Oh wait, it was 7/2 or something, right? Yeah, okay. All right. So now let me throw some BVP at you. And that would be the boundary value problems.
Just weird. Just switch the limits. Yeah, that's it. Okay, second answer.
Yeah. So for the boundary value problem, there's an A here. Remember, the boundary value problem has different starting points. And so our starting point, a boundary value problem would give you information about either y of A is equal to y sub A, and then y of B is equal to y sub B, whatever those numbers might be. But instead of starting at the same point, at 0 or x naught or whatever they want to call it, you're starting one of them, you have a condition on one, and then you have a condition on the other. Now, hopefully they give you conditions of just the original function, because they can conceivably give you y prime of A is equal to something and y prime of B is equal to something, or any combination of those. But I think in general they're just going to give you the original function's conditions at some starting and some ending points that would provide your boundary. So to solve for these things, you would get information. What's this say? Is that what I have in my notes? So your particular solutions can be found by integrating from the starting point to the ending point. Some spacing issues here. OneNote doesn't work as, yeah. Well, there he goes. Let's try to take a look at least start the problem in the last 3 minutes. Let's take a quick look at this boundary value problem. This is a boundary value problem. Yeah, this is a boundary value problem. And let's see what we can do with this. Six. So let's do things kind of quickly here. This is going to be a sign. So the homogeneous part, m squared plus 1 is equal to 0. So m is equal to plus or minus I. So it's going to be sine and cosine. So y1 will be sine x or cosine x. It doesn't matter, but I think we're used to doing cosine first. And y2 is equal to sine x. So to solve for your solution here, because of the boundaries, you would actually put 0 and 1 in there. So c1 cosine x plus c2 sine x. And then you're going to solve for c1 and c2 by using these boundary conditions. So using Green's theorem, we find the Wronskian like we did before. The Wronskian is going to be the cosine and sine. And I don't know if you guys have seen this already. We've done this already. It's going to be cosine squared plus sine squared, which is going to be 1. So that makes a nice Wronskian. And then your g of xt function is going to be equal to, it's going to be split up. And so we have to break this up to 2 different integrals for some x to be. And so we got cosine t sine x divided by 1, and then cosine x sine t for these values that are between 0 or between, I guess, 0 and 1. 0 less than t less than x, and x less than t less than 1. So you would have to integrate this and split this up going from x to a or b, or a to x and then x to b. All right. Yeah, maybe you guys can just look in the book and see what happens. Maybe I'll make a video of this problem and then post it online too. R0? Oh, wow. Okay. All right. See you guys on Tuesday.